Good morning. We have been discussing the Compton effect. Let me first recapitulate where our discussion ended in the last lecture. So, we have X-ray incident on a carbon target, and the carbon scatters the X-ray in different directions. The X-ray is incident at this from this direction as shown over here. Now, the particular X-ray source is such that it produces X-ray in a very narrow band centered around a single frequency. So, it produces a spectral X-ray spectral line centered around a particular frequency or wavelength in a very narrow band around this wavelength. And the quantity shown here is the spectrum as measured in different directions, that of the scattered X-ray in different directions. Now, if you look in the forward direction, the scattered X-ray is found only at the same wavelength as which was incident, but at other angles you can see that the X-ray spectrum, in addition to the wavelength that was sent in, it also exhibits another wavelength which is larger than the wavelength that was sent in. Now, if you try to interpret this in terms of X-ray being an electromagnetic wave, when the electromagnetic wave is incident on this carbon target, the electrons in the carbon, they are set into oscillation. They will oscillate with the same frequency as the incident radiation. An oscillating electron will emit radiation, and this radiation too will be emitted at the same frequency as the incident radiation. So, we expect to see only the incident frequency or the incident wavelength in the scattered light, in the scattered X-ray. But in addition to that, there is also this different wavelength, a larger wavelength component that is observed. Question is how to explain this. So, we have throughout this lecture been thinking of electromagnetic radiation as like for example X-ray as a wave, and every wave we know that these waves are oscillating electric fields which travels forward in time, and this can be represented mathematically using such a relation. Now, to explain this Compton effect, where you have Compton, this extra wavelength component that is seen is referred to as the Compton effect, and in order to explain this Compton effect, in order to explain this new wavelength component at a larger wavelength than the one that was sent in, it is required to invoke a particle like property to the X-ray. So, if you postulate that the X-ray behaves like a particle called a photon with energy h cross omega, where omega is the angular frequency of the wave, or h nu, where nu is the frequency of the wave, which you could also write as h c by lambda, the wavelength, and if you also attribute a momentum p h cross k or h by lambda into the direction of propagation of the wave so along with this wave, if instead of this wave you think of the X-ray, the incident X-ray as a particle whose momentum and energy are related to the angular frequency and the wavelength of the frequency and wavelength of the wave, like this, and let us see now if with this we can explain the Compton effect. So, there are the problem now is to be thought of as the photon incident on the electron is scattered in this direction, the photon gets scattered in this direction, and we have to apply the laws of conservation of energy and momentum and then try to relate the wavelength of the scattered photon with the wavelength of the incident photon, the energy of the scattered photon with the energy of the incident photon. The energy is inversely related to the wavelength. So, if the energy goes down, which you expect to happen in such a scattering, the wavelength is expected to go up, which is what we see. So, which is mainly the main reason why we think that with this kind of a postulate where the X-ray is made up of some kind of particles called photons, you can possibly explain the Compton effect, which is what we are now trying to calculate. So, we have in the last class we have gone into this calculation. So, the first thing that we invoked was the conservation of energy, and I had told you that the energy of the electron has to be calculated using this formula. This is the correct relativistic formula for the energy of the electron in terms of its momentum. And I had also shown you that this relation for the energy between the energy and the momentum gives you the usual Newtonian formula, half p square by m, with this constant rest mass energy also coming in. So, applying the conservation of energy, the initial energy was hc by lambda for the for the X-ray photon, and the energy of the electron, which is at rest to start with, is mc squared. This is equal to hc lambda prime by lambda prime plus the enhanced energy of the electron, because in this scattering the electron gains some energy. So, this has to increase because this energy of the electron has gone up. To maintain the conservation of energy, this energy of the photon has to go down, and by doing some algebraic manipulations on this, we have arrived at this expression, this relation between the momentum of the electron and the shift in the wavelength of the X-ray photon. Let me now next apply the conservation of momentum. This is the picture showing you the situation. Let us first consider the momentum along the x direction. So, the incident photon has a momentum h by lambda along the x direction. The electron has 0 momentum to start with. So, along the x axis, h by lambda, that is the incident momentum of the photon. The electron has 0 momentum to start with. This is equal to the x component of the scattered photon's momentum, which is h by lambda prime, and we have to take the x component, which brings in a factor of cos theta, plus p, the electron's momentum, cos phi. Theta is the scattering angle of the photon, right? That is the angle made by the scattered photon with respect to the direction of the incident photon. This is what we call the scattering angle. So, we have h by lambda prime cos theta plus p cos phi, and along the y axis the incident photon has no momentum along the y axis. So, the electron that comes out and the photon that comes out, their y momentum should exactly balance one another. So, the y component of the photon's momentum involves a sin theta, the y component of the electron's momentum involves a sin phi, and I can write down straight away that h by lambda sin theta is equal to p sin phi. Now, we have to do a little bit of simplification over here. So, let me take this onto the left hand side and square it. I will also square this expression. If I square this expression, what I will get is h square. Let me write it in the next page. So, I am going to take this onto the left hand side, so that this becomes a minus sign, and then I am going to square it. Once I take this on the left hand side and then square it, I will have this square plus this square minus 2 times this into this. So, let me write it down. What I will get is, along the x axis, I have, let me take h square common, and I have 1 by lambda squared plus 1 by lambda prime square cos square theta minus 2 by lambda prime cos theta. This is equal to p square cos square phi. So, let me remind you again, I have taken this on the left hand side and just squared this. So, I have the square of this, and the cross product. And along the y axis, I have, again I can take I have h square by lambda prime square sine square theta is equal to p square sine square phi. So, now I add both these expressions, and this will give me p square, and the left hand side is going to be this, these two terms cos square theta and sine square theta are going to add up to give 1. So, I have h square 1 by lambda square plus 1 by lambda prime square. These are the two terms over here, and now I can subtract. Let me write it like this. I can subtract minus 2 lambda prime. I can write it like this. So, I have written this term, the combination of this term and this term is what gives me this. I have added an extra term over here. So, now I have to I have subtracted an extra term. So, I have to add that, and I have to write this also. So, I can write it as plus h square 2 divided by lambda prime 1 minus cos theta. So, 1 minus this minus cos theta term is this, and this term exactly cancels out with this. So, this is the sum of these two terms. Now, note that this first term, the first term over here, can be simplified a little bit more. So, what I have is this is a whole square is 1 by lambda prime minus 1 by lambda whole square plus 2h square So, this I have written it in this way, and this expression you can see can be written as delta lambda divided by lambda into lambda prime square. So, this is this is the same as this, because I can multiply this whole thing by a factor of lambda and this by a factor of lambda prime. So, in the numerator I have delta lambda, in the denominator I have this square and this square plus 2 h square lambda lambda prime 1 minus cos theta is equal to p square. So, the conservation of energy finally gives me this. The conservation of momentum finally gives me this. The conservation of energy, which we had worked out in the last class, finally gives me this. So, I have to multiply this equation by c square if I want to compare it with the conservation of energy. Now, we can straight away compare these two expressions. This is the conservation of energy, this is the conservation of momentum. This term occurs in both the expressions, this term occurs in both the expressions. It essentially tells me that this term should be equal to this, because the other two terms are there in both the expressions. So, finally, what we have when I combine the conservation of energy and momentum is that this term should be equal to this. So, let me write it down separately and then we can proceed. So, what it tells us is that 2 h square c square 1 minus cos theta this is the conservation of momentum. This should equal to the term that occurs in the conservation of energy, which is 2 h c m c square 2 h c m c square into delta lambda lambda by lambda prime. And this factor of 2 is gone. H, one of the h over here is gone. So, this h square is gone, this c square cancels out with this c square, this lambda lambda prime cancels out over here, and what we are left with is delta lambda is equal to h m divided by mc into 1 minus cos theta, or this number h by mc is called the Compton wavelength. This is called the Compton wavelength. Compton, sorry. Lambda c, which is equal to h by mc. This ratio, or in brief, what you could write is that delta lambda, the change in the wavelength, is the Compton wavelength into 1 minus cos theta, where the Compton wavelength h by mc. So, what we have achieved is that we have been able to predict the expected shift in the wavelength if the X-ray can be thought of in terms of particles called photons. And we find that the expected shift in the wavelength is the Compton wavelength associated with the scattering particle into 1 minus cos theta. Let us go back to the situation that we are discussing. So, here we have X-ray incident on a carbon target, and in the carbon target we know there are these carbon nuclei and which has electrons around it. So, when the X-ray is incident on the carbon target, it is the nuclei as well as the electrons both are going to scatter the X-ray, both are charged particles, both are going to scatter the X-ray, and the shift in the wavelength that is going to be produced is the Compton wavelength corresponding to each particle into 1 minus cos theta, which tells you the angular dependence. Now, let us, you see the Compton wavelength for any particle. So, for the electron the Compton wavelength is going to be the Planck constant divided by c and also divided by the electron mass. For the nucleus is going to be hc divided by the nuclear mass. Now, the nuclear masses we know are much larger than the electron masses. The electrons are the lightest particles in the carbon sample, lightest charged particles. So, the electrons are the one which are going to be most effective in producing are going to produce the largest shift in the wavelength. They are going to be most effective in this process. So, let us estimate the Compton wavelength for the electron. Now, the electron, so the Planck constant so this is the Planck constant h and this is the Planck constant h cross, Planck constant. So, the value is given here, the electron mass, the value is given here 10 to the power minus 31 kg, 9.1 into 10 to the power minus 31 kg, and the speed of light is also known. So, let us put in the values, and so this, if you put in the values and calculate this, this comes out to be approximately 2.4 into 10 to the power minus 12 meters for the electron, and for the proton, neutron, the nuclei it is going to be much smaller. So, we see that that there is, if you assume that the X-ray, the incident X-ray comes in the form of particles called photons, the incident X-ray, if you think of it in terms of particles called the photons, and then calculate the energy transferred in this particle scattering, and then calculate the shift in the wavelength of the photon, then you get this prediction, and you find that there is going to be a shift in the wavelength which is of the order of 10 to the power minus 12 meters, a little more than that, and it is going to have a 1 minus cos theta dependence. So, let us first, so we have estimated the magnitude of the shift. Now, let us look at the angular dependence of the shift. What this predicts is that the shift is going to be minimum when theta is 0. When theta is 0, cos theta is 1, so this is going to cancel out. So, there should be no shift in the forward direction, which is what you see. The photon is not going to transfer any energy to the electron if it gets scattered in the forward direction, which is also what you see over there. And then as you look at larger and larger scattering angles, you expect the shift in the wavelength to increase, right, and the transfer of energy is going to be maximum to the electron is going to be maximum if the photon is scattered straight back. Then the electron is going to be imparted momentum in this direction, and that is going to be the maximum situation where the maximum energy is transferred to the electron. So, cos theta pi is minus 1, where this factor becomes 2, or the shift in the wavelength is twice the Compton wavelength. This is the situation when the maximum energy is transferred to the electron. which is also what you see. So, the pattern that you see here is very is quite close to what is very similar to what you expect from this qualitative discussion. The shift in the wavelength you can see here increases at as with theta, and this shows you at 45 degrees, 90 degrees, 135 degrees, and notice that at 135 degrees the shift that you see here is maximum. This shows you the same spectra blown up. So, this is the spectrum at 0 angle theta equal to 0, that is in the direction of the incident X-ray. So, the forward direction. So, there is only one spectral line seen over here. This shows you the spectrum at 90 degrees, this shows you the spectrum at 135 degrees. Now, the incident X-ray, the X-ray is incident at an angle at a wavelength which you can read from here. It is 0.0709 nanometers, 0.07. So, in this particular situation, the X-ray is incident and the X-ray which is scattered, the Compton effect, the larger wavelength, this is at, you can again read this from here, it is 0.0749 nanometers. And this is at 135 degrees scattering angle. So, when the scattering angle is 135 degrees, the delta lambda, the shift in the wavelength, is 0.004 nanometers. You have to check, you should check that this actually is consistent with the predictions of the calculation that we have done. So, you should check that if you put in 135 degrees over here for theta and put in the value of the Compton wavelength 2.4 10 to the power minus 12 meters, you can explain this shift in the wavelength which is observed. You get exactly 0.004 nanometers. So, what we see is that the photon picture, the Compton effect, if you wish to explain the Compton effect, you have to assume that the X-ray, that the electromagnetic radiation behaves like a particle. This particle is called the photon. So, you have to assume that the X-ray behaves like a particle called the photon, and the photon energy is h cross omega. It has a momentum h cross k, where k is the wave vector of the wave which you would have thought of, which you would have attributed to the X-ray if you had thought of it as a wave, and omega is the angular frequency that you would have attributed to the X-ray if you had thought of it as a wave. So, in order to explain this, these shifted wavelength lines, the lines with larger wavelengths, you have to invoke the assumption that X-ray behaves like that particle, and this is true not only for X-ray, it is true for the whole of electromagnetic radiation. So, the photoelectric effect, for example, which I have told you briefly yesterday, requires us to think of the radiation in ultraviolet visible or the blue end of the visible in terms of particles called the photons, and the same thing is required here. So, you have to now invoke the particle picture for light, for the whole of the electromagnetic spectrum. But this does not mean that you have to abandon the wave theory of light. If you abandon the wave theory of light, you cannot explain the phenomena of diffraction and interference, which we have been discussing extensively a large part of this course, and which there are many experiments which you might have, some of which you might have possibly done, where you have demonstration, clear demonstration of diffraction and interference using light, using electromagnetic radiation. Light, radio waves, all of them exhibit interference and diffraction. X-ray exhibits diffraction, and you cannot explain this without invoking the wave property of X-rays. But you cannot explain the Compton effect without invoking the particle, without assuming that the X-ray also behaves like a particle called the photon. So, what we see here is that light shows a dual behavior. It behaves like both a particle and a wave, and this is what is referred to as the wave particle duality. So, light behaves like both particles and waves. Whether it behaves like a particle or a wave depends on what you do with the light, depends on the context, depends on the situation, and you would have to invoke either the wave picture or the particle picture to describe the light. It is not that light is a wave and not a particle, or light is a particle and not a wave. Light is both. It behaves like both a particle and a wave, which is what we refer to as the wave particle duality. It exhibits both the properties of both. Sometimes it exhibits the property of a wave, sometimes it exhibits the properties of a particle. Now, this dual behavior is seen not only for light, it actually extends to everything in nature. Let me repeat this dual behavior that we have, which we have brought in to our discussion through the Compton effect, this dual behavior of light, that it behaves like a particle and a wave. This is not restricted to light alone. Such dual behavior is found in all of nature. So, this is found in all of nature. Let me write it down so that you get the point. This extends to all of nature. So, this is what we are going to discuss in the rest of today's lecture, and this is going to be what we are going to discuss in the remainder of all of the lectures that are going to follow. So, the rest of this course is going to be completely devoted to discussing this wave particle duality. So, all of nature exhibits this dual behavior, where it behaves sometimes like a wave, sometimes like a particle, depending on the situation, and this wave particle duality is what is going to be the center of our discussion in the lectures that are going to follow. It was so the Compton effect, I have told you, was discovered in, or I may have told you, was discovered in the 1920s. In 1924, the French scientist Broglie So, in 1924 the French scientist de Broglie, he hypothesized that associated with every particle we have a wave. What we have seen until now is that associated with every wave, for example, the electromagnetic radiation, it is sometimes necessary to think of it as a particle called a photon. Now, what de Broglie hypothesized was exactly the other way around. What he hypothesized was that for every particle, for example, for the electron, for this pen over here, or for any particle for that matter, there is an associated wave. So, for every particle there is an associated wave. So, let me write down a wave. We are all hopefully by this time familiar with how to write down waves, equations for waves. So, let me write down a wave. So, this is the wave, this represents a wave. So, what de Broglie hypothesized was that associated with every particle there is a wave, and this is what represents a wave. And the angular frequency of the wave omega is related to the energy of the particle through this h cross omega is equal to the energy of the particle, and the wave vector k is related to the momentum of the particle, just like we did for the photon. Or you could write this in terms of the frequency and the wavelength. So, the frequency is related to the energy, the frequency of the wave that is associated with the particle is related to the energy of the particle through this, it is E by h, and the momentum and the wavelength. So, the wavelength of this wave is related to the wavelength of the particle through this relation h by p, and this wavelength is called the de Broglie wavelength. This wavelength of this particular wave is called the de Broglie wavelength. So, let me again repeat what de Broglie's hypothesis was. His hypothesis was that associated with every particle there is a wave, and the angular frequency or the frequency of the wave is related to the particle's energy by a relation like this. The wavelength of the wave is related to the particle's momentum like this, and I have written down here an expression for a wave. And since we have been working in terms of angular frequency and wave vector, I have also written down these in terms of the momentum and the energy of the particle, and these are very similar to the relations we had for the photon. Now, the first question, so let us take up a few questions, but before we take up a few questions regarding this, there is a point which I should make. So, the point is a very important point. When we talk of a particle, whenever we talk of a particle, the position of the particle, its momentum, its energy, all of these are very well defined quantities at any given time. For example, if we discuss this pen and think of it as a particle, which would be appropriate if you were not interested in the orientation of the pen and such things, or you could take the cover of the pen and think of it as a particle, then its position at any given time, its momentum, its energy, all of them are very well defined. And when you write down the Newton's equations of motion for a particle, Newton's laws, it assumes that the momentum, the position, everything is well defined, and you write down second order differential equations, you solve them, and it will give you the trajectory for any later time. These are things which are familiar. So, for a particle, its momentum, its position, we know where it is, you know what speed it is moving with at any instant of time. And we expect a particle, you know that the particle is going to be only at one point. So, this particular pen cover is located at this point at present, at t, let us say this is t equal to 0. So, it is present, it is exactly over here. Now, if I leave it, its position is going to change and it is going to go somewhere else. So, there is no ambiguity as to the position of the particle at any given instant of time. It has a well defined position, it has a well defined momentum, and you can follow it at its position and momentum at all instants of time. There is no ambiguity about it. Now, you look at, let us look at the wave associated with the particle. So, associated with the particle we have a wave. Let us ask the question, where is this wave defined? Now, this question, the answer, you see this, let us look at this wave. Psi is a function of r and t, and if you give me any value of r, I will have a value of psi, and this is a sinusoidal wave. So, it is defined, if you draw it, let us say the wave, let us for an instant assume that the wave is along the x axis. So, if I draw the real part of this wave as a function of x, this is psi, the real part of psi, it will look something like this. So, if you ask the question, where is the wave is distributed all along the x axis, it is defined over the whole of space. So, the wave is not defined at any one unique point, it is defined all over space, the whole of space. You could have a value for the wave at any point, you could ask what is the value at any point. So, this particular wave is defined all over space. It has a well defined angular frequency and momentum and wave vector. So, and you can relate these to the particle's energy and momentum. So, the wave precisely represents the particle's momentum and energy, but this particular wave has no information about the particle's position, right. So, you see that there is a certain amount of ambiguity which is introduced the moment you think associate when you think of the wave, the moment you think of the particle as a wave instead of a particle, this wave contains only precise information only about the particle's energy and momentum. It has no information about the particle's position, because the wave is defined everywhere, it has no position information. This is an important point which you should note, and we shall discuss this point in more detail when we take up the interpretation of the wave that is associated with the particle. Next, let us calculate, ask the question. So, we were supposed to now take up a few questions. So, the next question that we are going to take up is, what is the dispersion relation for this wave? What do we mean by dispersion relation? We have already discussed this. A dispersion relation is a relation between the angular frequency and the wave vector. So, we know that the energy and the momentum for such a particle have a relation. So, let me write down the relation between the momentum and the energy. If the particle is non-relativistic, if it is moving slowly, we know that the energy E is p square by 2m, and the energy is related to the angular frequency of the wave as omega h cross. The momentum is related to the wave vector as h cross k. So, this is what it tells us, the relation between the energy and the momentum, and it gives us the dispersion relation, that this is equal to h cross k square by 2m. This is the dispersion relation. I leave it to you to calculate the phase velocity. You know how to calculate the phase velocity. You also have been taught how to calculate the group velocity. So, I leave these two things to you. You should please calculate the phase velocity and the group velocity for this wave. Now, I have what de Broglie hypothesized was that associated with every particle there is a wave. Now, the question is that when we think of a particle, when we see a particle, we do not think of it as a wave. There is no need for us to think of it as a wave, because at de Broglie's time there was no direct evidence that there is a wave associated with the particle. So, the question is then, on what basis was this hypothesis made? Was this hypothesis ever verified, or is it still a hypothesis? Now, at the time when de Broglie made this hypothesis, it was purely on theoretical and philosophical grounds, but it has later on been verified, and it is a very important development in our understanding of the whole of nature. So, let us go into it into a little more detail to get a feeling for what the wave, if there is a wave associated with a particle, we should make an estimate of what is the expected wavelength. So, let us start with an electron. Let us take a situation where there is an electron, and you might have heard of electron guns. These are there in TVs, in oscilloscopes. The electron gun is a device that accelerates an electron, and then the electron comes out with a particular speed. So, the way the electron is accelerated, there is a negatively charged metal plate over here, a cathode, and which is heated, and if you give a negative voltage to it, then the electrons will be emitted, and then here you can put a positively charged so, this has given a positive charge, and this has a negative charge, it is heated. So, it will emit electrons, and the electrons will be attracted, and then some of them will come out through, and they would have gone through a potential difference V, which will cause it to accelerate. The question that we are interested in is, suppose there is an electron gun where an electron is made to go through a potential difference V, what is the wavelength of the electrons that come out? Let us calculate this. So, the energy of the electron when it comes out, which goes through a potential difference V, is the charge of the electron into the potential difference, and the momentum of the electron is 2m into E, the square root of this. We are assuming that the electron is non-relativistic, so E is p square by 2m, or the momentum is P is a square root of 2m into the energy of the electron. So, we can now calculate the wavelength of the electron. This will be h by the momentum. So, h divided by 2m into the charge of the particle into the potential. So, I will write it like this, where V is the voltage, and what we have to now do is we have to calculate this number. So, the Planck constant we know is 3.34 10 to the power 6.63 10 to the power minus 34. The mass of the electron is 9.1 10 to the power minus 31 kgs, and the electron charge is 1.6 into 10 to the power minus 19 coulombs. So, if you use these values in this expression, what you will get is that this is equal to 1.2 nanometers divided by the square root of the potential difference. So, all that you have to do is you have to put in these numbers in volts, and if it is a 1 volt potential difference, the wavelength of the electron that comes out is going to be 1.2 nanometers. and if the potential difference is 100 volts, a 100 volt potential difference is not something which is very difficult to generate. So, if the potential difference is 100 volts, then the wavelength is 1 angstrom, right. It is 0.1 nanometers, 1.2 angstroms, but okay, approximately of the order of 1 angstrom. Let me make it approximately equal to 1 angstrom. So, what we see is that if we send an electron through a 100 volt potential difference, then you expect to get a wave. If de Broglie hypothesis is correct, you expect to get a wave of wavelength 1 angstrom. Now, if you compare this to electromagnetic radiation, 1 angstrom of the order of 1 angstrom is what you have where you have X-rays. And if you want to verify if the electron, whether the electron that comes out actually has wave properties or not, you have to look for some property, some phenomena which is exclusive to waves. And we have discussed quite extensively that two things which you cannot explain if you do not have waves, two things which you see only for waves are interference and diffraction. So, if by some means you could observe diffraction with this electron beam that comes out from the electron gun. So, you have an electron gun over here which produces a beam of electrons that come out. If you could somehow observe interference or diffraction with this wave, if with this electron beam that comes out, you would be able to verify that this is actually a wave. And the wavelength that you expect is around 1 angstrom, which you know is the wavelength of X-ray. So, this is not an electromagnetic wave, but its wavelength is comparable to that of X-ray. Now, X-ray we know exhibits diffraction when it is incident on a crystal. So, when X-ray is incident on crystal, which is what we have used, which has also been used in the Compton effect to study the spectrum of the X-ray, when X-ray is incident on a crystal, it exhibits a diffraction pattern, and the maximas occur whenever 2d sin theta is equal to m lambda. So, two scientists Davison and Germer in 1927, 3 years after de Broglie made his hypothesis, they used a large crystal of nickel on which they put an electron beam, and they found that there were, in the electrons that come out, they found a pattern of maximas just as you would if you had used X-rays. And this was clear evidence that electrons do have a wave associated with them, otherwise there is no way electrons can exhibit diffraction. Let me show you a picture of electron diffraction. So, this picture is very similar to the kind of thing that was done by Davison and Germer. Here an aluminum foil has been used, and this shows you the diffraction pattern that you obtain when X-ray is incident on the aluminum foil. So, when X-ray is incident on the aluminum foil, it produces a diffraction pattern. The aluminum crystals produce a diffraction pattern. The same aluminum foil, when there is a beam of electrons incident, it also produces a diffraction pattern, which is what is shown over here. So, the fact that you can have a diffraction pattern when electrons are incident on a crystal is clear evidence that the electrons also behave like a wave. And this is the demonstration of the fact that you need to attribute wave properties to the electron. So, in addition to thinking of electrons as particles, it is also necessary to think of electrons as waves. And it is not only electrons, for all particles there is a wave associated with it. Now, before we are going to discuss this extensively in the coming lectures, but before finishing today's lecture, I should there are a few points which I should make. The first point is as follows: in when we calculated the wavelength of the electron in the electron gun, we assumed that the electron is non-relativistic and the momentum and the energy are related as follows. Now, I have told you in quite detail that this is valid only when the particle is non-relativistic. If the electron is relativistic, if the electron moves very fast, it is necessary to use this relation between the energy and the momentum. Right, we have discussed this quite extensively in the last lecture. So, it turns out that if the potential difference is of the order of a few 10,000 volts, so few 10,000 volts, then it is necessary to take into account the full relativistic formula. If you are working at voltages below that, tens of thousands, then you can safely use this formula to calculate the wavelength, but once you cross that, then you have to use the full relativistic formula. The second point which I should make is as follows. So, what we have, what de Broglie's hypothesis is that the de Broglie's hypothesis is that associated with every particle there is a wave. Now, this obviously is counterintuitive to all of us, because whenever we think of massive particles, we do not think of the wave associated with it. For example, when I walk, or when I see somebody walking, when I see a dog walking on the street, I do not think of the wave associated with it. The question is why? Should I think of it as a wave which is there distributed, or should I think of it as a particle having a very well defined position? Why don't the wave attributes, the wave aspects of such a big thing, why do they not manifest themselves? Why does it not manifest itself, the wave aspect? Well, it is actually a very complicated issue, why in the macroscopic world we do not see this everywhere, we do not see this wave, the wave aspect, but we could make some preliminary estimates over here as to what the wavelength of the wave is expected to be, and that would give us some very crude idea of why we do not see the wave nature all the time for very big macroscopic objects. So, if for example, if I have a man walking, so let me take the weight, the mass of the person to be around 100 kilos, it will be typically less, but for simplicity I am taking it to be 100 kilos. Let me take the speed to be 0.1 meter per second. So, his momentum is going to be 10 kg meter per second. So, the wavelength is h by p, and this is going to be of the order of 6.6 into 10 to the power minus 35 meters, which you see is a very small number. The wavelength turns out to be extremely small. Right. So, I think that is sufficient discussion for today. Let me stop here. We shall resume on this topic in the next lecture.